Hi, I'm Blake, and welcome to the Physicist's Guide to Success. Sorry, I've been on a bit of a hiatus. Had a lot of midterms and a lot of stuff to do, but let's just jump into this section. So this is going to be work energy plus potential energy, and we're just going to be going over the details surrounding it. So let's pretend you want to describe how a force and the amount that object moves due to that force are related. So what physicists did a while back is they said, okay, well, let's see here. So we have a force, let's pretend it's like this, right? That's going to be the force. Then we have here the amount the box or the object actually moves. Like that, right? That's we're going to call this S. Just why not? So what physicists did is they say, well, we can't really just multiply this together because that wouldn't make any sense. Like, these values could mean a bunch of different things, and we don't really know how they relate, because if they're going in opposite directions, what do we do? We multiply by negative? What do we do? It makes all this confusion, and they didn't really know how to approach it. But they did find a way. And essentially what they did is they broke these things down. So here we have the force F. Well, we're going to break that into its X and Y components. Oh, why did I draw an arrow? I'm going to break it up into its X and Y components. There's the Y. And we also break the distance moved in its X and Y components. Or whatever its perpendicular components are, it doesn't matter. Why don't we keep on drawing a line? Here. So, essentially, we isolated its components. It's a vector. So, we can just break it up into its components. And what they did is they said, well, why don't we just multiply the components together? I mean, that makes the most sense. Because it directly correlates directly correlates the force done in one direction with the amount it moved in that direction. So it decouples. If we do it this way, that means that the force in Y is affecting the force in X. What physicists are doing here now is that we're just saying that the force in X and the distance moved in X are going to be only relying on each other, and that a force in the Y or distance moved in Y is not going to affect anything in the X direction. And that makes sense. If you push a box, let's say you push this box over here in this direction and it goes up, that isn't really going to be you. You're not causing that work. But we'll get into that stuff in a bit. So if we multiply this stuff together, it's going to be f of x, s of x, plus f of y, s of y. This seems really familiar. If you remember at the beginning of the semester, we actually had something that's very similar to this. It's the dot product. So we have here the vector of the force and the vector of the distance moved is going to be this. And wow, that's pretty cool. But this only looks at a certain moment. This only looks if either S is linear or at one very specific chunk of S moving. But what if S is like, let's pretend if the distance moved is like that. Well, how are we going to even calculate that? We can't really just say it's this, because what about the distance here? Well, we could actually say that it's going to be F dotted with ds, so a small change. And then we can sum up all of those changes to find the total amount of work. And boom, there is our equation for work. Pretty genius, right? But before we go into this, let's reimagine this part, the physical intuition part, because that's the most important. You always have to understand what this actually means. So let's pretend, let's go back to the same box example, right? You have a box here, and you're pushing with all of your might. This is a weird looking dude. But you're pushing with all your might onto this box. And you're pushing at this force. But then for some reason, the box starts floating for some reason. It just starts to go up. Whether it grew wings and it was actually just a pigeon, or if it just was like air from it, like one of those vents that just like that pushes the box upwards. Well, it shows that your contribution is actually not doing any work. It's actually just something else, another force, a mysterious force that's doing all the work. Just think of it like this. Let's pretend you're doing a group project, and you decided, I don't want to do much for this, so let me just write my name in each of the page that my other group members did, and just call it a day. Well, when that project is turned in, you're not going to be doing any of the work. Other people are doing work, so your contribution, aka the force in this situation, you might be doing something by writing your name, but your actual work inside of that project is 0. And it's something similar here. And so that's just a way to break it down. So we have this, right? Well, what is this? What is this? Something more intuitive that we can grasp onto? Because I mean, like this is cool, but like, what is this even? How can we relate this to something that we know or something that's more intuitive? Well, let's look at this. Okay, so let's look at this left-hand side of the equation. So we can't really assume anything about ds. I mean, we can't really assume anything about this term, because what if there's no force in the x direction? Or what if s is like this, but f is like this? We can't really assume anything. There has to be a cosine there then, because there's this angle here. So what do we do? Well, let's do something cheeky. Let's just break this up into each direction. So we'll have f of x dx plus f of y dy plus integral of f of z dz, you know? Well, then what we can do is we can just substitute everything in here. So we know that a is actually just dv dt, right? dv dt, and v is x dx, plus m dvy dt dy, plus integral of m dvz dt dz. Well, that's cool. But then what can we do about this? Well, if you remember from Calculus 2, or even just like any of the other calculus classes, you remember that the chain rule, right? dA dc is going to be equal to dA dB plus dB dc. So essentially, if you just, or sorry, not plus. Why am I doing this? It's going to be multiplying. So if you multiplies it out, let's pretend like this were like regular numbers. These will just cancel out, and then you're just going to be left with the same thing. It's just like multiplying 2 over 2, kind of. But yeah, so let's do that right here. Let's factor. Well, since mass is constant, we're assuming that mass is constant. Be aware of that. We can factor out the m out of all the integrals, and then it just becomes the integral of dv dx dx or dvx dx dx dt dx. Ooh, that's a lot. Plus integral of dvy dy plus, or not plus, not plus, dy dt dy, and last but not least, dv z dz dz dt dz. Now I'm getting dizzy all just writing this out. So this just becomes, this is just velocity in the x direction, this is velocity in the y direction, this is velocity in the z direction. And then this cancels, so you end up just getting vx dvx plus integral Vy dVy, or yeah, dVy plus Vz dVz. And since these terms directly match up with those here, we just get 1/2 m Vx squared plus Vy squared plus Vz squared. Now, doesn't this look kind of familiar? Well, if V was really a vector that contained of components Vx, Vy, and Vz, well, this would just be its magnitude squared, right? Because the magnitude is just the square root of this square, adding the squares of these. So then if we just square that, it will just give you adding them without the square root. So then that just becomes the magnitude of V. Also, integrated at endpoints. So at state 1, state 2. So you get here 1/2 m V squared at 2 minus 1/2 m V1 squared is equal to the work, or in other words, the change in kinetic energy. This is kinetic energy, and I'm pretty sure you've seen this before. It's pretty famous, and rightfully so. It's a pretty nifty quality, and it basically shows that the work done is the change in kinetic energy. So that's saying that moving and changing the, essentially either the mass, or, well, we're not really going to be looking at the mass here, but because of our assumption, but just looking at how a object's velocity is changing, that's going to be pretty important, because it's going to show you how the work is changing. So if you put work on an object, that means that this has to change. If there's if there's work being done on the object. So that's pretty important. And that's going to be one of the equations you'll have in your toolbox now. Especially useful in certain problems where it's just like find the work. Okay, yeah, well, yeah, it's just, you'll see how it applies, because this is going to be getting into even more stuff later on. But before we go into the other stuff, there's going to be a lot of questions that ask you to look at a graph, just practical stuff. Sorry that I'm switching up notation here, and I'm using the little arrow on top. I got used to vector calculus. Now they want you to do that. So if we look at this, if let's pretend the force was only in the x direction and the distance moved is only in the x direction, then this just becomes f of x dx. So let's pretend you have a graph showing the force with the distance. So it's just x. Well then, due to the properties of integrals, if you want to find the total work after it's moved this much, then it's just the area under the curve. Okay, that's good. Yeah, okay, that's all. And that's just because of stuff you learn in Calc 2. Okay, so now let's look at the potential energies. So, where did this energy come from? I mean, if there's kinetic energy, what about the other types of energy? Well, there are other types of energy. For instance, pretend you're on the Leaning Tower of Pisa and you drop a ball. And it falls, and it's right about to hit the ground. Well, it's moving really fast. The change in the kinetic energy is super high. But there has to be something to compensate for it. And from this example, you can definitely see is that it drops a lot. And it drops due to gravity. So there's going to be a change in some sort of gravitational potential energy. So yeah, let's say this, because the change is always going to be a change. But the kinetic energy essentially goes up, but the gravitational potential goes down. Gravitational potential energy goes down. So from this, we can really just see that in a system where energy is always maintained and matter is always contained in an isolated system, we can see that the change in kinetic energy is going to be the change, a negative change in the potential energy. So in other words, kinetic energy plus potential energy is equal to 0. This is only an isolated system. So no energy is flowing in, no energy is flowing out, no mass is flowing in, no mass is flowing out. So if that's true, that means everything is self-contained. Energy cannot be created or destroyed. Voila. Everything, the energy inside the system has to be the same. So let's look at the main types of energy, or potential energy you'll be seeing. First, gravity. Here's the free body diagram of a ball falling. Okay, so let's find the work here. The work is equal to the integral of the force dotted with ds. Well, ds is just going to be dy, but this force is not going in the y direction. It's going in the negative y direction, so it's going to be negative integral of mg dy. And as it's going from state 1 to state 2, so we're making a definite integral, so state 1 to state 2, it's going to be the negative mg y2 minus mg y, or plus mg y1. So you can also think of it as mg y1 minus mg y2, or in other words, work is equal to negative change in gravitational potential energy. So we're going to call this, if we just look at it like this is its gravitational potential energy at some point, and then the change is its change. There's this. So if that's the only force acting on the body, then work is equal to negative that. Pretty interesting. So in other words, too, same thing. Kinetic energy is also the change in that. And that makes sense with our Leaning Tower of Pisa example, because that energy is being converted. Another thing. Let's look at this. Let's look at a little box here, right? And it's attached to a spring. But let's pretend it's really stretching on, like let's pretend this is its equilibrium position. But then suddenly it's stretched out like a huge distance. It's exerting a force. It wants to go back to this equilibrium position. You've seen this before. You've seen Hooke's law before. If you draw a free body diagram on this, there's going to be a force trying to pull it back to the equilibrium state. It doesn't want to be this. It doesn't want to be stretched. You know, every object has that compression or just expansion force, because it doesn't want to be squished, doesn't want to be pulled. This is equilibrium. Okay. So it's pulling this way. So if we do the same thing, work is equal to F dotted with ds. Same thing here. We know that Hooke's law is kx, right? Kx dx. It's going to be kx, right? So why kx? Because Hooke's law is kx. And of course, x is just referencing x minus x naught here. So essentially, how far it is from its regular equilibrium position is how much it really wants to move. So as you get farther away, it's going to be a big force trying to push it back in, but as you get closer to this equilibrium position, it's like, oh, maybe I don't want to move that much. I'm just only displaced a little bit. So let's be really diligent here, and then just call this k x minus x naught dx. How do we integrate this? How do we integrate this? How do we integrate this? Well, we could always do a u sub and just call u is equal to x minus x naught. But we could just, you know, distribute it, and we'll be here. Well, actually, no. Let's just do a u sub. That makes things a lot easier. U is equal to x minus x naught. So then du is going to be equal to dx. Okay, simple. Oh, and I forgot the negative here, of course, because it's going in that direction. Okay, so this just becomes W is equal to negative KU to U. So then it integrates to negative 1/2 K delta U. In other words, negative 1/2, just writing out the full thing, 1/2 K x1, x2 minus x naught squared plus 1/2 K x1 minus x naught squared. In other words, negative change the elastic potential. Okay. So we found here that the work is equal to the negative, and this is negative potential energy, and that fits in with what we said before. And we said how we said that the force, or not the force, sorry, that the change in the kinetic energy or the change in work is equal to the negative change in potential energy. That's interesting, you know. But that only happens if those are the only, if those forces are the only ones acting on it. What if you have like another force, like friction or air resistance? Then what happens? Well, then that becomes a non-conservative case. So let's define conservation first. A conservative force is one where the path doesn't matter, as it only relies on the endpoints. So let's pretend you have gravity here, right? Gravity doesn't care if you just go like this or like this. The gravitational potential energy only cares about the change of this. If you're looking at air resistance though, and this ball is like whizzing through the air, it's losing energy because the ball is colliding with those air molecules, and it's just losing a bunch of energy when it's colliding. So that's a lot of energy it's losing, you know? Okay. So it's losing energy. So if we want to fit this into our equation, we'd have to say that the change in kinetic energy, we can actually do a proof of this, but I'm pretty sure you'll understand where I'm coming from. Plus work other is equal to 0. So this is the same conservation of energy system, except with a closed system. So energy is allowed to float and flow out, but matter is not. So essentially we're saying here, the kinetic energy plus this change in potential energy plus the energy lost to the environment is equal to 0. Conservation of energy statement. Boom. So you're often going to be making a lot of statements regarding this. So you're going to say, like, if you want to really expand this, I can say that kinetic energy at state 2 plus, I don't know, mg y2 plus 1/2 k delta x2 squared plus work other is going to be equal to ke1 plus mg y1 plus 1/2 k delta x1 squared. And you're going to be using this statement a lot when you're dealing with non-conservative. So work other is what we consider something non-conservative. So the friction is not conservative, you know. We can go into a proof about this too, but I'm pretty sure you can understand this just by like intuition. If you push an object here, let's pretend that you have like a box, right? And you push it over here, and then you push it back. The friction isn't going to be like, oh, you worked harder in one direction, let's make it slippery so you don't have to do as much work in this direction. No, it's going to be, well, I'm going to pose you this way. I'm going to pose you in the same direction. It's non-conservative. It doesn't rely on the endpoints. It relies on the path taken. But then on the other hand, there's something like gravity, where it's just like, let's pretend you have an inclined slope here. The box moved there, and then it moved back. Well, you gained gravitational potential energy, but then you also lost it when you went down. So it's conserved. That's conservation. Pretty neat stuff. So you're going to be using all these equations you're going to be using in some form for work energy. Last but not least, we have here, what does this look on a graph? Well, in a graph, we have this. So this is just our regular statement of, okay, let's okay, so this is what our graph is going to be looking like. So let's pretend you have here like a force graph, right? And so it's like this. So if you don't know, okay, actually no, here, let's have it be U. So let's pretend you have a graph of the potential energy at some point. The gradient, which is this triangle right here, is just going to be the partial derivatives in terms of x plus the partial in terms of y plus the partial in terms of z. This is vector calculus stuff. Some of you haven't taken it, but it's okay. So you can just look at it in one direction. It's just going to be a regular derivative. So essentially what this is saying is that here are these, so here's u and here's x. So what this is saying is that the area under this, or, oh, so not the area, because it's going to be the derivative. So the derivative, so essentially is when this change is the most, like when the slope is the steepest, that's when there's going to be a force. It's going to be a big force. But when this is flat, then that means that there's going to be no force. The force is equal to 0 here. Yeah. But the thing is, though, this isn't just going to be the force. This is going to be the negative force because of this. It's going to be the negative. So essentially this is saying the derivative of the potential energy graph is going to look like the negative force. Just something to keep in mind. You never know if you're going to get a question like that. So that's basically a lot of just what work energy theorem, conservation of energy, potential energy, that's all that it is. So I hope that you had a good idea of what this is. I'll try to put out an example problem if I can this week. I'm not sure. Yeah. This is the Physicist's Guide to Success, signing out.